Good. All right, so the next presentation will be by me on the Hexa-X-II project. I hope, Sharif, can you keep track of time, please?
Of course, yes.
Thank you. So the Hexa-X-II project is a so-called European flagship project. So it's an enormous project with many partners. It started in January 2023 and is running till middle of next year, and it focuses on the 6G platform and system as a whole. So rather than focusing on specific technology, it covers all of 6G. It has 44 partners. Nokia is the overall leader, and Ericsson is the technical manager. And we cover a very large consortium across the value chain, including academia, SMEs, and large enterprises, basically covering everything that associates with 6G. In this talk, however, I cannot cover all of 6G. I will only focus on the aspect of JCAS, or Joint Communication Sensing. So this is a little bit different than what other projects call integrated sensing and communication. We use the term JCAS, but it means the same as integrated sensing and communication. I will briefly talk about the foundations of joint communication sensing, the different modalities that we are studying, how it relates to the different radio enablers in 6G, and then I will go into a little bit of detail on the Hexa-X-II activities on JCAS before wrapping up. Since Hexa-X-II is such a large project, I cannot go into much technical detail, but I refer you to the Hexa-X-II website and the deliverables for more information. Let's start with the foundations. So JCAS, or integrated sensing and communication, integrates sensing and communication into a single system. And as the previous speakers already mentioned, so sensing is a rather broad term, and it corresponds to processing radio signals for specific services such as radar-like sensing or positioning. And then positioning can be interpreted as a service running on top of sensing. We distinguish in Hexa-X-II between positioning and localization, and we call positioning when we refer to determine the coordinates of a connected device, while localization can also include a passive object, such as device-free localization. We're considering different integration levels in Hexa-X-II for joint communication sensing or integrated sensing and communication, ranging from reusing the same radio sites to reusing the spectrum, reusing the same infrastructure, to reusing the waveform, and all the way down to reusing the same time frequency resources. And all of these are potential versions of integrated sensing and communication. As we will see later, we are considering also trade-off and synergies between sensing and communication. So trade-offs could be in terms of sharing the same radio resources. Whatever you give to sensing, you take away from communication. And then synergies are more at a higher level. By providing sensing information, you can improve communication efficiency. The benefits of JCAS as compared to having separate communication and sensing systems is, of course, that you reuse the hardware, you have a conservation of resources, and you also have this immediate cross-functional advantages of using communication for sensing and sensing for communication. We are considering a variety of metrics, and these are typically different from the communication metrics, such as accuracy, latency, availability, detection probability, and resolution. Of course, since we also consider communication, we also consider the typical communication metrics like rate and spectral efficiency. Complementing the traditional KPIs, so the key performance indicators, we are also considering the KVIs. So these are the values of 6G, such as sustainability, inclusiveness, and trustworthiness. Here, sustainability could, for instance, mean that we use very efficient AI methods that require less training, or that we use position information to reduce energy consumption for communication services. Inclusion could include the use of non-terrestrial networks for spanning coverage to areas that could not be covered with other systems. And trustworthiness relates to aspects of security and privacy, and in general, trust of the 6G system. For more information about how KPIs and KVIs can connect, I refer you to this paper here, linked below. JCAS has a variety of applications, as already was mentioned in the presentation from Etsy. The primary use case is probably to improve the communication itself, for instance, to beam from in a direction where you know there's a user, or to avoid blockages. Other important applications include UAV and drone management and safety, detecting illegitimate drones in airspace, smart transportation applications such as platooning, industry applications such as autonomous robots and human interaction, and also digital twinning. And with all these applications come, of course, extreme requirements. In Hexa-X-II, we're studying different JCAS modalities. These include monostatic sensing, bistatic sensing, and multistatic sensing. And for each of those, we're considering the different versions. So monostatic sensing could be initiated by the base station, but it could also be initiated by a user, or it could also be initiated by what is called a positioning reference unit. So this is a user device that has a known location. In all of these cases, you need some full duplex capabilities, which could be a limiting factor. More compatible with current system is bistatic sensing, where the transmitter and receiver are physically separate. And then you could have bistatic sensing between two base stations, which of course is typically not compatible with traditional duplexing systems, or bistatic sensing from a user to a base station, or vice versa, or between two users. With all of these bistatic sensing modalities, especially when a user is involved, you have to be aware that the coordinate systems play a role. So for the sensing information to be useful, you need to know where the users are. And finally, we're also considering multistatic sensing with multiple transmitters or receivers that are physically separated. This could also involve users in the sensing process. And here, an important consideration is how to synchronize the different units. We're considering both time synchronization as well as phase synchronization, for instance, in a DMIMO context. So JCAS is one of the radio enablers that we're studying in Hexa-X-II, but we're studying much, much more than that. So here is a list of the so-called radio enablers that we are considering in Hexa-X-II. This is taken from one of our recent deliverables, early results on 6G radio key enablers. So in addition to JCAS, we're also considering different frequency bands, including the lower bands, mid-band, FR2 millimeter wave, as well as sub-terahertz. And for each of these, the sensing capabilities are, of course, different, providing different levels of range and object penetration capabilities. We're also considering reconfigurable intelligent surfaces or meta surfaces, and these can improve positioning and sensing performance by providing around the corner capabilities or sensing and positioning when there's line of sight blockages. We're also considering non-terrestrial networks, so this includes satellites, UAVs, to provide sensing and positioning services in remote areas. And their important challenges relate to, for instance, the high mobility of the satellites and the corresponding Doppler shift, which must be mitigated by the user. Other are maybe more traditional systems built on top of 5G, such as massive MIMO, where we use large array apertures to provide high angular resolution, which is very relevant for both positioning and sensing. However, this requires precise calibration to be useful. We're also looking at distributed MIMO or self-free MIMO systems, where you would have an extremely large aperture if you have phase-coherent stations, because then they would operate like a very large array, which provides another way to get resolution in addition to delay and angle resolution. And finally, we're looking at artificial intelligence as a methodology to improve sensing performance. For instance, to do calibration of hardware impairments, to perform sensing and imaging, to detect objects and classify different kinds of objects, to also learn new kind of signals at the transmitter side rather than using traditional directional beamforming. Maybe we need new beamforming that are optimized for JCAS. And we're also looking at doing compact representations of sensing information useful for limiting backhaul transmissions. So the point of this slide is that while in Hexa-X-II we're studying many aspects of 6G radio, JCAS can connect to all of those. So now let's go a little bit deeper into the JCAS activities within Hexa-X-II. And then in the meantime, I hope you're enjoying all the AI-generated art. So the JCAS activities in Hexa-X-II span different aspects. So on the one hand, we have the hardware level, so we focus on the hardware enablers. Then we have the radio level, considering models, deployments, waveforms, and signal processing. And then we have the architecture level. So how can JCAS be supported through the proper functions and protocols? The figure here is taken from a recent paper in the Proceedings of IEEE, where we cover JCAS in a broad perspective, though not considering the functions and protocols. So I will go through each of these three levels in a bit more detail now. In terms of JCAS demonstration, one of our partners, namely Qualcomm, is working on using communication waveforms. These are typically modified OFDM waveforms, so from 5G standard, and they are modified to support higher bandwidth to use for joint communication and sensing in a bistatic context. So there's a transmitter and receiver, they're physically separated, We're sending OFDM waveforms from one of the to the other. And with that, we try to map objects in the environment. And we're trying to map both the static object as well as the moving object in the environment. And this allows us to showcase that we can reuse the same hardware and we can actually provide very accurate sensing capabilities. We have specific targets which are provided in our deliverables. We also have an associated activity which relates to gesture classification. So this is a use case where there's, again, a bistatic setup with a transmitter and receiver physically separated. And we have users that are moving, making different gestures, for instance, for game control, but also this could be for supporting elderly people or people with reduced mobility. And then we use machine learning to classify different gestures. Results for all of these are available partially in our past deliverables, but also will be coming up in our next wave of deliverables, which are due in February. We also have done a study on JCAS channel models. So we have considered what does a channel model need to support in order to evaluate JCAS use cases. So these different JCAS features or requirements are shown as different columns in this matrix here. So for instance, we need to be able to have objects in a common coordinate system. We should be able to support different types of objects. We should support radar cross-sections at different frequencies. We should support the use of extended objects, so which have maybe separate scattering centers. We should support mobility of both the communication devices as well as the objects that are moving in the environment. And all of this, of course, should be in a common coordinate system. When looking at extended space and time, everything should be spatially and temporally consistent to provide meaningful models. We should be able to support near-field effects, such as channel non-stationarity and curvature of the wavefronts. The channel model should also be able to support generating different data sets, for instance, for this gesture classification use case. And of course, the communication and the sensing channel, they're physically the same channel, so they should be fully compatible and reciprocal. We then evaluated the existing channel models that are available, for instance, the statistical geometric models, like the ones used in 3GPP, ray tracing models, hybrid models, and then stored channel models in terms of these requirements. And from this, of course, we can see that some of those requirements can be met by some of the models. And our conclusion is basically that hybrid models or ray tracing models may be preferred for future evaluations, including in 3GPP. We've also studied different deployment options. So for instance, in Hexa-X, we looked at NTN, REES, massive MIMO, and DMIMO. And we looked at how each of those could be related to JCAS. So how could the REES support JCAS? How could NTN support JCAS? And so forth. In parallel to these deployment options, we also looked at the different more signal processing enablers and waveforms. So we've performed JCAS waveform optimization. So these are typically not completely new waveforms, but we rather use OFDM waveforms, and then we optimize them in terms of power allocation across time, frequency, and space. So here space would refer to beamforming. We've also performed AI-based design and processing. So we design optimal waveforms for JCAS using AI, and then we could design the corresponding receiver-side signal processing or classification methods using AI. We also have some security studies related to the localization of jammers. And we also studied inter-user protocols for joint communication and sensing. Again, due to lack of time, I cannot go into detail into all of these, but you can find a lot of information in our extensive deliverables on the Hexa-X-II website. So this is really at a radio level, and I think also the previous presentations kind of stick to this radio and hardware level. In Hexa-X-II, we also look at a higher layer. So we look at what is JCAS data? How should we manage this data? How should we collect this data? And JCAS data is not limited to just the radio JCAS data, but also external data, so-called non-3GPP data. You can think of camera data, LiDAR, radar, or even GPS. And we need, of course, interfaces towards the network functions to support sending this data around and collecting this data. And this turns out to be very challenging because these interfaces are different. The data looks different. There's different levels of trust differentiation. Data comes asynchronously, has different latency requirements, different storage requirements. And there are also different data consumers. So all of this needs to be controlled and managed. Interestingly, the JCAS data is a new kind of data. So it looks like user plane data. It is not control plane data, but it is not tied to any specific user. So maybe we need a new kind of data plane or a new kind of plane for the JCAS data. And then also the JCAS data needs to be collected, but it also needs to be cleaned and properly labeled. So considering the JCAS data, once it's kind of collected at the reference point, is a very complicated process. And to address this, there's a central role of the so-called sensing management function. So the sensing management function is expected to replace the current location management function and to deal with the sensing control, configuration, and the data processing. So here is a more detailed view of the sensing management function. This is shown here in this orange blob here. This receives an external sensing request, for instance, to sense object in a certain environment. Then the sensing control function would select the corresponding sensing method. For instance, this base agent should perform monostatic sensing. It would also need to do discovery of all the units around, including base stations of end users, and then does resource selection. So how many resources in terms of time, frequency, power can be allocated to the sensing process. Then the sensing data is collected. It should be processed, and this is done by the sensing processing unit inside of the sensing management function. And then the sensing data is then exposed to the external user of the sensing data. And the sensing management function can be centralized, but it can also be partially distributed because maybe part of the sensing processing should be done at distributed units. An important consideration for all of this is security and privacy. For instance, maybe you don't want to be sensed in a certain area, and if you don't have a device, how can you control that? We have performed an exhaustive evaluation Hexa-X of both security and privacy using the so-called STRIDE framework for security risks and the so-called Linden framework for privacy risks. And you can find more details of this evaluation in this paper linked here. But this brings me to my conclusions. I understand that I had to stay at a very high level because we have so much material in Hexa-X-II. But in conclusion, we want to have JCAS to support new services that combine sensing, positioning, and communication, which can improve communication service, but also unlock new capabilities. Importantly, it will reduce capital and operational expenses compared to having a separate communication and a separate sensing system. JCAS has implications, of course, at the radio layer and as well as at higher layers. At the radio layer, it interacts with all the other radio enablers, including REIS, meta-services, non-terrestrial networks, AI, distributed MIMO, massive MIMO, and so forth. At the radio layer, it's our view that there are only trade-offs between communication and sensing because whatever resources you have, you need to share them. So this is a kind of finite cake. So when you take something for sensing, you have to give it away to communication. One thing I didn't really talk about in detail, but is that communication is less sensitive to hardware impairments than sensing. So this is something that needs to be treated carefully in terms of calibration and modeling. And then at the higher layer, there are both trade-offs and synergies between communication and sensing. The synergies emerge because the communication service can use sensing information collected previously to avoid blockages or to perform beamforming. The sensing management function will play an important role to handle the request, the processing, and also deal with privacy and security aspects. And basically, these security and privacy aspects will be a major concern for supporting JCAS services. With that, I end my presentation, and for more information, I'll refer you to the JCAS, for the Hexa-X-II website. Thank you.
Thank you so much, Henk, for the great presentation. I think we have 2 or 3 minutes, so if you have any questions, please send them over. I think we have just received one question here. What is the difference between localization, positioning, and sensing in JCAS research literature? I am a little bit confused. So Henk, maybe you can talk a little bit about that.
Yeah, so I think many people, they combine positioning and localization as one term, which means the determining the location of a connected device, like a smartphone. Here we intentionally kind of separated those because positioning is also used in 3GPP to refer exclusively to determination of a user device. So that is kind of how we think about splitting positioning and localization. But other people can think of this differently. So for some people, localization and positioning are the same. And then sensing in Hexa-X-II mainly refers to radar-like sensing, like the figure I show here on the right. So this is a kind of radar image showing a range Doppler plot with different targets. But sensing can also include weather sensing, pollution sensing, imaging, and so forth. So I think it's a bit of a wild west out there where people use different terms in different ways. These are just the terms that we used in Hexa-X-II.
Perfect. Thank you, Henk. Maybe another question. So 6G is expected to be rolled out by 2030. That's roughly 5 years from now. What do you think should be are the top challenges that should be on our agendas as academics and industry to solve by that time so that we can actually have ISAC as part of 6G when it gets rolled out?
I think to me, the fundamental challenge is really this calibration, synchronization, dealing with the hardware aspects. Because the communication industry typically did not have to face this. Because for communication, you can be quite relaxed about what is the orientation or tilt of antenna panels, but they are very crucial for sensing and for positioning. So this, I think, will be one of the main challenges.